Good evening to everyone. Let's start today's session. Welcome to the fourth week for the live interactive problem solving sessions for the course on Python for data science. I am Sedu Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. Okay, so far in the past 3 weeks, we have been looking at the basic programming concepts in Python, and also some of the core libraries that are used for data science tasks. Right. So today, so we'll be putting all those concepts that we have learned so far into actual modeling for some data sets. Right. So how we'll see how to use Python for actually doing the data science or data analytics models. Right. So how do we build models? How do we use it for prediction? How do we understand the models? So those things we will look at it today. So let me share the notebook. Okay, so in week 4, we were looking at two kinds of problems. One is a classification problem, and another is a regression problem, right? So these are the two broad kind of problems that you will typically encounter when you are using machine learning. So there are other kinds of problems. So like these classification and regression problem comes under the class of problems called supervised learning problem, right? So where you are given some data, right? So where you'll have some values, some variables measured about different observations, and you would also have recorded the response or the output for those observations. So the task is in a regression model, it is the output would be a continuous variable, right? So for example, if you want to predict the price of a house, so based on certain features about the house, so we'll call it as a regression problem because we are trying to predict a continuous value, right? So we are trying to predict some real number. So those kinds of problems, we'll call it as regression problems. And the other class is the classification problem, where here again given some attributes about some observations, we are trying to categorize that observation into one of several classes, right? For example, if you are looking to classify emails into a spam and spam email or a not spam email, so that would be a classification problem, right? So here the output is not a continuous variable, it would be a categorical variable, right? So we are trying to predict the output class, right? So which is a predefined set of categories. And in particular, if we have only two classes, right? So example, in this case, it is either it is spam email or not spam email. So if it is two classes, we call it as a binary classification problem. All right. So the other thing is when you have more than two classes, it would be multi-class classification problem. So these are the two kinds of problems that you'll be looking at. And so let's start. So first, let us import the required libraries that we'll be using in today's session. So apart from what we have seen so far, cmat.lib, numpy, pandas, and cbond. So today we will be using the scikit-learn library. So to install scikit-learn, so you have to do pip install scikit-learn. Okay, so this is the name of the library that is available on the Python packaging index PyPy. And so you have to install this first before you start following this. And scikit-learn is a very popular Python library for machine learning tasks. So it comes with several algorithms, machine learning algorithms available, right? So it is very easy, and also there is a lot of community support for it. Plus it is also open source library. So we should definitely learn about scikit-learn. And once you have installed scikit-learn, to use it, so we'll actually use this name instead of scikit-learn. We call it as sklearn. Okay, so this is the name from package name that from which we'll be importing all the required functions. Okay, so we'll look at what are these different things. So as we go on, so we'll be using some data sets. So scikit-learn comes with some preloaded data sets for us to just test different models, right? So we'll be looking at different models, and also it comes with functions for evaluating your models, right? So different criteria are used for evaluating regression models and classification models, and also functions for optimizing your models for selecting the best parameters for your given data set. And also there are some visualization tools that help you understand how uh, these machine learning models are working. So yeah, so let's move ahead. So first we'll start with the classification problem. So for this classification problem, so the data set that we'll be using is from the scikit-learn library itself. So there are some toy data sets that scikit-learn has, so which comes with the library. So when you install the library, so these data sets are also part of it. So you can directly load those libraries. These are small in size, so maybe around less than 1,000 observations we can say in each of these different data sets. Whereas it also provides you with some functions, helper functions, that will allow you to download some actual real world data sets from the internet, right? So those are also available. So for these details are available in the scikit-learn page. I have given the link to it. You can look at it once I make this notebook public. So for now, we will, for the classification problem, we will load a toy data set. So this is called as the iris data set. And for this, I'm just importing this load iris function from the sklearn datasets package. Okay, so to get this data, all you have to do is call the load iris function. So what it gives you back is this iris, right? So I'm storing it in this iris variable. If you look at the type of this variable, it says that it is a object of type sklearn bunch. So a bunch is nothing but a dictionary. So scikit-learn's way of returning this data sets is in this bunch object, which is very similar to a dictionary. So if you look at what are the attributes and attributes that are associated with this using the dir function, you see that there are some these are the different attributes that are associated with the bunch object. Right, so there is DESCR, so it comes with a description of what this database is. So the actual data, which we'll call it as features, right? So it's stored in this data key, and also the target, which is the output variable, right? So it's stored in the target key and so on. So if we look at what this iris data is about, so I'm just printing the description attribute. So this is a data set which contains about three varieties of plants, iris plants, right? So these are iris setosa, iris versicolor, and iris virginica, right? So three different kinds of plants. So that is our target variable, right? So we are calling it as class, right? So each observation. So there are 150 observations in this data set. Like each observation belongs to one of these classes of plants, right? And there are some attributes. Attributes are features. So these are the explanatory variables, right? So these describe about those observations. So we have four numeric features, so which are used to predict the class of the plant. So what are those four features? So one is the sepal length, so which is given in centimeters, the sepal width also in centimeters, and also the length and width of the petals, right? So these are the four features that we have, and these are numeric variables, right? So these are in centimeters, and the output is a categorical variable, so the observation can belong to one of the three categories, right? So therefore this is the classification problem that we are dealing with. And also this is a very balanced data set. So what do I mean by balanced is, so the number of observations that we have 150. So out of this, so there are 50 observations that belong to one of these three classes, right? So we have equal number of observations for each of these three classes, right? So on the contrary, an unbalanced data set would be where you will have majority of observations belonging to a few set of classes, and the remaining classes would have a relatively fewer number of observations, right? So those are called imbalanced data sets. So that can create an issue when you're making models. So there are techniques, but we will not be covering those things in this particular session, how to deal with those imbalanced data sets. Right, so moving ahead, they also give some summary statistics of these different features. So we have the min, max, the mean, and the standard deviation of these length and widths for the sepal and the petal. and also we have some correlation with the different the classes that we have. And there is no missing data in our particular data set, right? So, but we have seen in the previous sessions, if there are missing values, how we will deal with it. So again, we will not look at those aspects in this particular session. And yeah, as we already see, there is the distribution is 1/3 of the observations are there for each of the classes, right? So this is a balanced data. So they'll give some more information, so you can read about this later, like what this actual data set is actually about. Okay, so now we saw there are other kinds of attributes that are there in this bunch object. So the one that we are interested in is the data attribute, right? So this data is actually the features, right? So we have the 4 features, right? Sepal length, width, petal length, and petal width. So that data is given to us in the form of a NumPy ND array, right? So if you look at the shape of this array, so it is 150 by 4, right? So 150 is the number of observations and 4 columns. So these belong to each feature that we have. So if you look at this, so this is the data. It's a 150 by 4 NumPy array, right? So each row corresponds to one observation and each column corresponds to one particular feature, right? And these are numeric variables. So if you look at what are the 4 features, the names of the features are given in the feature names attribute. So the first column corresponds to sepal length, second sepal width, third petal length, and the fourth one is the petal width. So what I'm doing is for ease of working with this data set, I'm going to convert this data from a NumPy array into a pandas data frame. Right. So how can I do that is I'll call the data frame class, and then to its constructor I'm just passing in the NumPy array that we have. So that is the data, and I'm passing what are the names of the columns that is contained in this data, and this would return me a pandas data frame. So I'm converted this NumPy array into a pandas data frame, and it's just the same values that we already had, right? But just in the data frame format. And then what is our prediction is about? So we are going to try to predict each of these observations into one of 3 classes, right? So for each observation, what class it belongs to is contained in this target variable. Okay, so we have numbers here instead of the class names, right? So we saw 3 classes, but what we are given with here is numbers. 0, 1, and 2 are the 3 unique numbers that we are seeing. So each number corresponds to one class, right? So 0, 1, and 2, these are the 3 classes. But what are the names of these classes? So that is given in the target names variable. So 0 corresponds to the class Setosa, 1 corresponds to versicolor, and 2 corresponds to Virginica, right? So these are the 3 classes, and each observation belongs to one of these 3 classes, right? So first 1/3 of the observations that we have are belonging to Setosa. The next 1/3 corresponds to versicolor, and the last 1/3 corresponds to Virginica, right? So that's how our data set is. Again, I'm converting this target, NumPy array into a pandas series. So instead of data frame, I'm just calling the series class, and to its constructor, I'm passing the target variable. And the name, since this is a single column, the name of that would be class. I'm just naming it as class. Okay. So I've converted the NumPy array into a pandas series. Okay, so before we start building the model, so once we have the data set, so at this part you will be exploring the data set, and then if there is any cleaning to be done, as we saw in the previous session, you would do that. And just before you start building the models, what you have to do is you have to split this data set that you have into 2 parts at least, right? So those 2 parts correspond to what we call as the training data, and other part would be calling it as the testing data or the evaluation data, right? So why we divide this into these 2 parts is right. So when we are trying to train these machine learning models, so we'll be using the training data, right? So for the training, what we will do is we will tell the model what the features are, so which is these attributes, right? So for each observation, we are going to tell the model these are the different features, and we'll also be telling what is the actual class that those observations belong to, right? So for example, we will say for the first observation, so these are the sepal lengths and the petal length and petal widths, and the the class that it belongs to is 0, that is Setosa. So we will be telling both the features as well as the target values when we are training the model, right? So the model will try to learn how to given a set of features, how to tell which class it belongs to based on the observations that we are providing with, right? So in the training data. And if once we train the model like that, and then if we want to evaluate it and we try to evaluate it on the training data, then we would be getting a biased result because the model has already seen what those output classes are, right? So it would not be a good way of evaluating the model if we try to see how good it is on the training data itself. So what we will do for evaluating how good the model is in predicting, so we would be using this other set of data that we have, the testing data, and see how is the model that is trained on the training set performing on the test set. Okay, so that this would give a good indication of how well this model is able to generalize to data that it has not seen earlier. Okay, so that's the purpose of splitting it into training and testing, right? So for example, if I have to give a simpler example, if I am teaching someone who doesn't know how to do addition, and I'm teaching them using some example, say I'm saying 1 plus 1 is 2, right? And if I want to test them whether they have learned how to do addition, if I ask them again what is 1 plus 1 and they say 2, it could be because they have learned how to add two numbers, or they could have just memorized if it is 1 plus 1, the answer should always be 2, right? So I will not be able to tell whether they have learned how addition is done or whether they have just memorized, the output is just 2. So to test that, I have to ask them some other example, right? Using addition itself, I should ask what is 3 plus 5, and if they say 8, so it means that they have memorized. They have not memorized the answer, but they have learned how to do addition, right? So that's the purpose of doing this train test split. So how do we do that splitting? So again, scikit-learn gives us functionality for this. So there is a function called train test split, which is within the module model selection, right? So from sklearn.model selection, we can import the train test split function. And to do the split, what we have to do is we have to pass in the data, right? So the x values are the features, so we have stored that in iris features data frame. So I pass the input features, and next I pass the target variable, so which is a panda series here, and then I say what should be the size of the test set, right? So I'm giving it as a fraction. So 0.3 means 30% of the observations should belong to the test set, and the remaining 70% will be in the training set. And by default, what this train test split function will do is it will try to split your data set by randomly picking the observations, right? So instead of saying instead of taking the first 30% to be test or first 70% to be trained, what it will do is it randomly picks 30% of the observations to be in the test set, and the remaining 70% would be in the training set. And because this is random, so every time you run this function, you will get a different split, right? So therefore, to have some reproducibility, when you run this again, or if you want to share this with somebody else and who wants to also get the same result, so we'll be setting this parameter called random state. So so we'll give some number. So this is used to seed the random number generator that this function will be using in the background. So by setting this random state, what we are making sure is that we will get the same split every time, even though it is trying to make some random split, we'd be getting the same output every time. But if you remove this particular parameter, you will get different outputs each time, right? So just for reproducibility, I'm going to set this random state to 42, and its output would be, so first the features, it would be split into two parts, the training and the test part. So that would be the first two output that we will be getting, and the next two output would be the target variable, which would be again split into the training part and the test part. So you'll get four outputs, so the feature split and the target split. And if we just look at the size of these outputs, so we see that the training data has 105 observations and the testing data has 45 observations, right? So this is in the 70-30 split. Okay, so there are some questions in the chat. Yeah, in the exam, so you'd be asked about the classification and regression problems. So this notebook will be shared in the Google Drive. So the link for that, you can find it in the Google Sheet that is available on the course page. Okay, so Shubham, test size and random state. I don't know what is your question there. Okay, why we write shape 0? Okay, so why did I do shape 0 here? So if you look at the shape, it will give you the size along each dimension, right? So since the output X train iris is a data frame, it has two dimensions, right? So one is the row dimension, other is the column dimension, right? So if you look at the shape attribute, so there will be two values. So one is how many rows are there and how many columns are there. Like here, I want to know, the set size is basically the number of observations, right? So I want only the first value in the tuple, right? So therefore, I'm just indexing using the indexing operator and then selecting only the first value. So because the indexing starts at 0, I'm choosing the first element using the 0th index, and that gives me the 105, which is the number of rows. Okay, so you should be able to unmute. So it is enabled. So you should try again or try to log out and then log in again. Okay, so moving ahead. So now once we have the data set, so we have the splits for training and testing, we can now try to actually go about building the models.
So the question was here, particularly on test size, which I've used in the trains split while splitting,
Okay.
test size and random state. So I wanted to know the difference between these two.
Okay, so test sites basically tells you, how to, how many observations should be there in your training set and how many observations should be there in your test set. So it's about the number of observations, right? So here, when I gave 0.3, so if you see, there is, there were 150 observations, right, in total. So 30% of that is 45 observations, right? So that's what I'm getting in the test size. I'm getting 45 observations in the test data, and the remaining 105 observations are belonging to the training data. So this ratio is represented by the test size. So if I change it to say 0.5, so in that case what will happen, I'll get an equal split, 75 and 75. So that's the role of the test size variable. So it is just to tell you how many observations will be there. The random state is is for controlling which observations will belong to your test and the training data, right? So, for example, okay. So what I have done is I'm just looking at what are the observations that are there in the training data, right? So this is with the 30% split under random state 42. So what I'm getting is, so there is the observation number 81, the index of the observation, the 81, 133, 137. So these belonging to the training data. But let us say if I remove this random state, so what happens? So the size is still the same, right? So because the test size is 0.3, so the ratio is still the same. But if you look at the observations that are belonging to our data, you see that it has changed, right? So instead of 81, 133, we have some other observations that are belonging to it, 80, 79, and so on. If I run this cell again, right, so I'm still not given any random state. You see again it has changed, right? So if we do not, specify a random state, each time we are calling this train test split, so we'll be getting different observations belonging to the training and the test size, right? So because it will randomly pick the observations each time we run it. So if I want some reproducibility, if I want the same observations every time I run this, so I have to specify a particular random state, right? So again, when I mention random state as 42, I'm getting the original, like whatever I showed for the first time, right? So 81, 133, 137. By fixing the random state, you'll get the same observations in the train and the test set, right? So that's the difference between the test size and the random state.
Does 42 have any relevance, or you can use any
No,
other number?
you could choose any number. 42 is just for this example. You can choose any number, it doesn't matter. As long as you have the same number, you should get the same output. But if you change the random state, you will get a different output. So if I say 50, I'd get a different set of observations. But every time I run it, I'll get that particular one. So 1742, if I run it again, I'll again get the same thing. So for one random state, you'll get one set of observations. So that will be the same every time you run it. But if you change the random set, you will get a different set.
Okay, and the test size that you told right now should be zero point 0.3, right? So
Yeah,
how do we decide that it should be zero point 0.3 or zero point 0.7 or zero point 0.5?
yeah.
On what basis?
So there is no standard rule that tells you this should be the test size. So the idea of the test set, as I said earlier, it is just to see how good the model performs on an unseen data set, right? So we are just picking up some portion of your data. So ideally, the test size should be smaller than your training size, because you want large portion of your data available for the model so that it can learn the patterns, right? So typically, you would keep the training data to be 70% or 80% of your total size of your data set, and the remaining for the testing purpose, right? So around zero point 0.2 or zero point 0.3 is are some of the usual values that people would pick, right? So because you want a large portion of the data for the model training, because larger data would allow the model to pick up the data patterns in the data. So if you have very small training data, so then the model may overfit. It will learn some noisy information that may not generalize well. So the thumb rule is you have to keep most of your data for training, and the rest of it for testing. So zero point 0.2 or zero point 0.3 is some conventional value that people use.
Okay, okay, thank you.
Okay, so moving ahead. So for this classification problem, so again there are different models that are available even within scikit-learn itself. So just to illustrate how these the scikit-learn API works, I'll show this using two models. One is a logistic regression, which is a simple linear model, and the other one is a decision tree classifier, which is a tree based model. Irrespective of what model that you are choosing, so these models are called estimators in the scikit-learn library. Irrespective of which estimator you choose, scikit-learn follows a very repeatable or very uniform API for all its estimators, right? So this is the fit and predict pattern that you will see in all the estimators. So what these fit and predict mean is, so to train the model, so you'll be using the fit function that belongs to those estimators. And once you have built the model, to make predictions using those using the built model, you will call the predict function. So these are the two major functions for each estimator or model that you will need, right? And the input parameters that these fit and predict takes is also consistent across the different models. So for fitting any particular model, you will be calling the fit function, and you will pass the x and y. So x is nothing but the input features. So in our case, this is the data frame that contains the sepal length, sepal width, petal length, and petal width. Right? Those are the explanatory features. So that is called as x, right? So the features are the input data, and the y is the target variable, right? So in the classification problem, it would be the class labels. In the regression problem, it would be the output value, right? So that is the input that the fit function takes, the x and the y, and what it would give you is the model that is fit on this data. So one particular example is, for example, if you want to use this logistic regression, we would be importing it from the linear model package, right? So, and then we would first create an instance, right? So instance of this estimator. So when we call logistic regression, right? So we'd be getting an object of this particular class, and on this returned object, the estimator. So we'll be calling the fit and then pass in our x and y, right? And then because we have split our data, and this is the training portion, so for fitting, we'll be using the training portion of our data, right? Like the X train and the Y train. And once we have, fit the models, once we have made this call to the fit function, so to make predictions, we'll be using the predict function, right? So again, just like fit function, we have the predict function. And what we have to pass in is only the input features, right? So because the prediction gives you what the class labels are, you don't have to pass the labels, only the input features. So once you give the input features, the output would be the predicted class labels, right? So to make that, it's very simple. You just have to write one line, so which is the model that you have fit dot predict, and then pass in the data. So here we want to evaluate it on the test data, right? So we pass in the input features corresponding to the test set that we have split, and the output would be the corresponding class labels, because this is a logistic regression model, right? So that's that. This is this and this fit predict is uniform for all the models, like the linear regression that we will see later on, the decision tree, even for the random forest ensemble models, the support vector machines, all of these different algorithms that are available in scikit-learn follows the same pattern. So you just have to just remember this pattern, and then you can use it on any of the model that you are trying to use. Yeah, so those exam questions, you please write it to NPTEL, because I'm not aware of how the exam will be conducted. So you please write it to NPTEL support. They will be tell you. Okay, so now let's build a logistic regression model. So if you look at the help for the logistic regression, so this is you can do it in the Jupyter notebook by using the question mark and then put the name of the object. The logistic regression, I imported it from the scikit-learn linear models package, right? So from sklearn.linear models, I have imported the logistic regression. And if you look at the the help for that, so it tells you what are the different parameters that are available, right? So there are number of parameters that you can control in order to make this model fit well to your data. So what this logistic regression does, it does either the binary classification or multinomial regression, and if it is a multi-class output. So because we are dealing with three classes, so we'll be doing a multinomial logistic regression. Right, so you can go through this, what are the different parameters and what do they mean. So all those things are specified, what each parameter does. So just to get started, with all the default values for these different parameters. So as I showed, you just have to, create an instance of that particular, class. So here we just call the logistic regression, create an instance for that particular estimator, and then fit the model. So we are using the training and the training features and the training labels for this iris dataset. So once you run that, so you have now fit the model, right? So the model fitting is done. So the training part is over. So in order to make the prediction, so we will call the predict function, right? So and here I'm making the predictions on the test data, right? But you can also use the training data. It doesn't matter, right? So but as I said earlier, predicting or evaluating it on the test data is more appropriate.
Is log under reg a data frame?
No, it is the model instance of the logistic regression model, right? So it's not a data frame, it's the model itself.
Okay. Okay.
So it is
Can you just run this x underscore train underscore iris separately and y underscore iris separately, so that we can just relate how the fit is getting done between those two data train data?
sorry, I did not get your question. Can you repeat?
I'm saying that we have included in the round brackets of fit as x underscore train and underscore iris. So they are two different data frames, right? Or training data, right?
Yeah. So this is your input
So,
data. So this is your features and this is your target value.
okay, can you run it separately on two different lines, so that we can understand that what is getting fit into each other?
Yeah, so you can't split this into two lines, right? So this has to be together, because this is a single function call, right? So you have to pass in both x and y together. So this, we are telling these are the input features. Right, so these are the input features. There are 4 features. All right, so for these observations, and the corresponding, so for each of these observations there is a corresponding target variable, so which tells us which class those observations belong to, right? So we have to give both of these together to the model for it to learn the patterns. So when you're calling the fit, you have to give both x and y together. So what
it is saying that against 81, means it is saying against 81 the y training is done for 1 or 2, it can be, right?
Yeah,
basis on the speaker length and everything, right?
yeah. So what it is telling us. So for this observation number 81, so these are the characteristics of that particular plant, right? So for a sepal length of 5.5 centimeter, width of 2.4, and a petal length of 3.7, and a petal width of 1, the class that it belongs to, the type of the plant is 1, right? For another observation 133, which has these characteristics, right? So the type that it belongs to is 2, right? So that's what we are telling. So given a
Okay.
particular
Have
combination,
we converted that categorical data into numerical data previously?
yeah. So
Because I'm
what we got originally from the load iris function is was already in the numerical format. So when we loaded the iris dataset from the scale-learn datasets, so the target variable that was given to us was directly in the numerical format. So this iris.target was already encoded in this numerical format. But if it was not in this format, you should convert it into this numerical format,
okay. Okay.
because
Okay.
you
Got
can't
it.
pass
Thank you.
in strings, right? So these algorithms cannot work with strings. So you should, if it was like for these first one third, if it was setosa, and the next one it was versicolor and magenta, you should convert those strings into unique labels, numerical labels.
Yeah, while splitting it will cause an error, right? To convert that
No,
string to
splitting
float,
it, while
right?
splitting it, it won't cause an error. When you are fitting the data, fitting the model, it will throw an error.
Okay. 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 Yeah, thank you.
Yeah. So once we have fit the model, so we can use it for prediction by calling this predict function. So for prediction, all you need is only the input features, right? So you don't have to pass in the target variable, because that is what the model is trying to output, right? So when you run the predict function, you see, if you see the output, so it gives you a prediction for each observation in the test data, right? So in the test data we have 45 observations, right? So for each of the observations, our model is giving you a prediction. So it says that the first observation belongs to class 1, the second observation belongs to class 0, third belongs to class 2, and so on. Right? So this is the predicted values, right? So but actually you can, so here it's a categorical output. Directly it tells you one class out of three, but you can also get the probabilities associated with these three classes. So actually what the model does, it will try to get the probabilities associated with each class. So the actual predictions before it converts into this categorical value is the probabilities for each observation. So for each of the 45 observations, so there will be three values that the model will be predicting. So these three values are the probability that the model thinks that that particular observation belongs to that particular class. So if you see the predict probability function output instead of the predict output. So you'll see values like this. So for the first observation, so there are three values given, right? So this is the probability that that particular observation belongs to class 0, the probability that observation belongs to class 1, and the probability that the observation belongs to class 2, right? And if you sum up all these probabilities, it will be 1, right? So because it has to belong to one of these three categories. And what here the model does is it will pick the the class that has the highest probability to be the output. So for example, if you compare these three values, the class 1 has the highest probability among these three, right? So 4 into 10 power minus 3, 8 into 10 power minus 1, and 1 into 10 power minus 1, right? So the largest value is 8 into 10 power minus 1. So the output is 1, right? So this is how confident is the model is on that particular observation belonging to a particular category, and the class on which the model is more confident about is output as the the output category. Okay, so for the second observation, if we see, the class 0 has the highest probability, right? So 9 into 10 power minus 1, followed by 5 into 10 power minus 2, and 5 into 10 power minus 7, right? So this is the largest value. So the model is thinking that it belongs to class 0, and that's what you get as the output here, right? So you can get these probabilities using the predict probability or the predict prob function, right? So again, you just have to pass in the input features. So now once we have made these predictions, so how do we evaluate this model? So for classification, so there are a number of metrics that are available, like very obvious metric is the accuracy score, right? So we know beforehand which is the category for these test observations, right? So that is available in our y test. So this is the true category, right? So we know that this observation number 73 belongs to class 1, right? So that is known to us. And then we can compare what the model says for this particular observation, right? So that is in our predicted y-pred log rate, right? So we know the true values for each observation, and we also know the predicted category for each observation. And accuracy is basically looking at what percentage of the observations are we correctly classifying, right? So for example, if for the one observation, only one observation was correct, let us say only the 73rd observation where the predicted class is matching to the observed class, and the rest of them the predictions don't match. So in that case, 1 out of 45 observations are correctly classified. So that would be the accuracy score. Right. So here what we are looking at is basically how many observations the predicted and the actual class matches. So that we can do by calling the accuracy score function. So this is from the sklearn.metrics package. Right. So we have to pass in the true labels, and then you have to pass in the predicted labels. Right. So that will give you the accuracy score ranging between 0 and 1. So if you want it in percentage, you can multiply this by 100. So because this is a very simplistic example, right? So the logistic regression model is able to predict perfectly. So you have a 100% accuracy. This means that the model is able to correctly classify all the observations in the test set. Right? So this is a very good model, right? So because this is a very small example, so the logistic regression model is able to perform really well. And the other way, there are other metrics as well, like precision score, recall, and F1 score. So those are different methods of evaluating. So there are some limitations associated with accuracy score, especially when your data is highly imbalanced. But you can read that up, to learn about the different metrics and how do they perform. But that doesn't matter. So in order to use those, you'll follow the same pattern. So you'll import the corresponding function from the metrics package, and then pass in your true observation, true class, and the predicted class. So one way of visualizing the classification models performance is using confusion matrix. So what confusion matrix gives you is a plot like this. So where you have a 2D matrix, so the y-axis corresponds to the true labels. So we have three classes. So there are three labels. So those are the three plant classes: Setosa, versicolor, and virginica. And the x-axis tells you the predicted labels, right? And the values in the cells tells you how many observations belong to that particular combination, right? So when the true label was Setosa and the predictor label was also Setosa, so we have 19 such observations where that combination is happening. So for 19 observations, the model is able to correctly say that it belongs to the Setosa class. And for 13 observations, the model is able to say that it belongs to the versicolor class, and again for 13, it belongs to the virginica class. Right. So this is all the observations that we have in the test set, right? So 45. So basically the model has not made any error, right? So if we have anything, any number on the non-diagonal cells, so those are incorrect observations, right? So if it is true label was Setosa, if the model predicted versicolor, so that is an incorrect prediction. So that would be coming up in this particular cell, right? So but in our example, so we do not have any incorrect predictions from the model. So these are 0, and all the diagonals are only filled. So this is a perfect prediction, the perfect result that we can get from this particular model, right? So this is one way of visualizing the performance of the classification model. And to do this, so we are using the confusion matrix display class from the again sklearn's I think it comes in the model selection, or in the matrix package itself. So from the matrix you can get the confusion matrix display, and so it has a from predictions method, so to which you can pass in the observed class labels and the predicted class labels. And if you do not pass in the names, right, so it will just use 0, 1, 1 and 2, because it does not know the class names. So, but you can fix that by telling what these names of the classes are. I'm just passing the names of the targets that the iris dataset had, and therefore you'll get a very well formatted figure like this. So that's all there is to get a model built and evaluating in sklearn, right? So you have to split the data, you have to clean the data, make it into proper format, split it, and then call the fit function. Choose an estimator, call its fit function for training the model. And once the model is trained, you can call the predict function for making the predictions with it.
How would we get to know that the model has been trained? Is it dependent on the accuracy score, or it is dependent on the confusion matrix?
Uh,
Means we can just rely on that.
yeah, so you have to look at the different metrics. As I said, accuracy is one of the metrics. You can look at other metrics like the F1 score or precision and recall, depending on what your target is. And by looking at those the metric values, you can decide is the model performing good or not. And if it's not satisfactory, you can go back and try to change the parameters of the model. Like for example, here, as I said, there are multiple parameters, right? So that are available for the logistic regression, right? So we have only used the default values, and still we got a better fit, right? So that's why we are not going to tune this model, tune these parameters of the model. So we are going to leave it at this here, but we'll see some other examples as we go forward. So where we'll try to we'll try to build a base model with the default parameters, and we'll try to tune the model to get better performance.
Okay. Thank you.
Okay, why are we using both linear regression and logistic regression for fit and test? So we have not used linear regression, so we are only using the logistic regression estimator. So for both fitting as well as the evaluation. So if you look at it, so for fitting the model, so we have used the fit function from the log-reg estimator, right? And for evaluation, so for making the predictions, again we are using the same estimator that we fit, and then but calling its predict function. So we are not changing the model; we are using the same model for both fitting and evaluation. The stopping criteria depends on the model that you use, right? So different models have different algorithms used for training. So for the logistic regression, again, it uses a numerical data numerical method solver. So in this particular, by default, it uses the LBFGS solver. And yeah, so there are different values like the tolerance. So here it does in multiple iterations, and when the improvement is less than this particular tolerance value, it will stop training the model. So again, it varies from a function to function, but as long as you are using this scikit-learn API, you don't have to worry about that. So the API pattern is consistent. Is there any way to see the model parameters like learning algorithm, number of hidden layers? Yeah, so the particular number of hidden layers. So these again, it depends on the model, how it is defined, right? So the number of hidden layers, so those comes with the deep learning models, the neural networks. So this logistic regression model doesn't have such kind of hidden layers. So you can see the coefficients of the model. So this is because we have four input variables, right? So it has these are the coefficients that correspond to those variables. Because we have three classes, so there will be one utility function in the logistic regression corresponding to each of the three classes, and this is the corresponding coefficient of the four variables that we have used. Again, this is highly model specific. So if you take a different model, you'll have different parameters, right? So it depends on it, but you will be able to see what those values are once you have fit the model. Yeah, it will be the classification of the regression problem, but you should be knowing about other algorithms as well. So there are k nearest neighbors, linear regression, ensemble models, support vector machines, and so on. So you can just go through the scikit-learn library, familiarize yourself with what are the different algorithms that are there and which is suitable for which ones, which cases, limitations, advantages of these things. But it would be a classification or a regression problem. Okay. So we have seen logistic regression for classification. So I'll just show you how easy is it to just change the estimator, right? So for the same data, if you want to use a decision tree classifier as the estimator, so the only change that you have to do is actually change the estimator. So instead of a logistic regression, I'm just going to create an instance of the decision tree classifier, and the rest of the steps remains exactly the same. So once you have created the estimator, we just have to call the fit function on it, pass in the training data, and then once we have fit the model, so we can just predict it exactly in the same way by calling the predict function on it, right? So that's how easy it is to use sklearn because of its consistent API for all the estimators. So here we have fit a decision tree classifier. We have made the predictions now, and we can estimate it in the same way. So again, this decision tree classifier is also giving us a perfect prediction, right? So on the test set, it is achieving 100% accuracy, which means for all the observations, the predicted class matches the observed class. So we can still make all these visualizations. So there is no change in how you would go about, training or, using the models for prediction, right? So you just have to use the fit and predict methods and use the corresponding metric for that particular problem. And you'd be able to, use the different models that are available. So that's all there is to it in using this. So we'll just move ahead with the regression problem, right? So as we saw earlier, so the difference between the classification and the regression problem is in the type of the target variable that we are trying to predict, right? So in the classification, we have a categorical target variable, whereas in the regression problem, we are going to predict some continuous value. So for this regression, we are going to use, look at a problem where we are trying to predict the price of the houses. So we are going to use the California housing data set. So this is a real world data, right? So this is not a toy example, but an actual data. And so this, data has to be downloaded. It does not come with scikit-learn itself, but scikit-learn gives you utility function which helps you download this data set, right? So again, there is this fetch California housing function which is from the sklearn.datasets package. So you use that, and then when you call that, it will return you the data. After that, if it is not already downloaded, it will return the data to you. Yeah. And so I'm just passing in this as frame is equal to true, parameter, and I'm calling this. So to simplify, the process of, converting the data. So earlier when we did not pass this, when we are loading the iris data, we got the, the output of this in terms of numpy arrays, which we had to convert it ourselves into data frame, right? But there is also this as frame parameter. If you set it to true, it will automatically give you the data set in the data frame format instead of numpy array format. So if you look at the description for this data set, so here we have 20,640 observations, right? So this is quite large compared to what we worked with earlier, right? So the iris data set, it was only 150, but here we have a quite a relatively larger data set, and we have 8 numeric predictive attributes, right? So instead of 4 features like we saw earlier, so in this particular data set, we are going to use 8 features, and these are the features that we have for each observations. We have the median income. So this is the median income in a block group, right? So here the basic thing is, so we are having in the California district, so which is divided into different blocks, right? So, and for each of these blocks, so there will be multiple houses that are present in it, right? And each house is going to have some sale value, and we are trying to predict what is the median value of the houses in that particular block, right? And therefore we are going to describe the blocks, each blocks in this California district, And the first one is the median income. So among the different people that are living in that block, what is the median value of the income, that those people in that particular block earn. And then we have the house age. So this is again, of all the houses, what is the median age of the house, right? So for how long has that house been present. Then the average number of rooms that are present, per household, right? So you have the number of rooms would be differing by the different number of houses, and the average number is given in average rooms. Then average number of bedrooms. So this is particularly looking at number of bedrooms in that house, and population tells you how many people are living in that particular block. Then there is average occupancy, which is out of all the household members, how many people are working, and then the location of that particular block group, so the latitude and the longitude of it. So based on these attributes, our target is to predict what is the median value of the house prices for belonging to that particular block group, right? So therefore, you can see that because the prices are a continuous value, right? It is not like it is 1, 2, or 3, but it would be some floating point number, right? So because the prices is a continuous variable. So that therefore this is a regression problem that we are addressing here. And the target value is the median house value, and it is expressed in hundreds of thousands of dollars, right? So if the price is median price is say 400,000, then the target variable would be 4, right? So because it is in units of hundreds of thousands of dollars. So let's look at the name of the target value. So it is the median house value. If you look at the target variable, so it is like this, right? So it's a continuous value. So for first observation, so the value is 4.526. So which means that it is, so the actual value should multiply it by 100,000. So it is $452,600, right? So that is the actual, target value. So this is the variable that we are trying to predict. So let's do some small exploratory data analysis. So if you look at the data frame, the input data, so we see that the 8 columns are there, and we do not have any missing values. So if you have missing values, you have to do appropriate treatment, to address that. And all these are numeric variables, right? So we do not have to do any conversion here. And what I'm doing is I'm just creating a data frame by concatenating the input features and the target variable for some plots that you will be making next. So I'm just concatenating the target variable to the data variable, and then creating one data frame out of it. So just this particular column has been added to the input features. And first I'm going to look at a pair plot. So pair plot will give you for each combination of the variables in your data frame a scatter plot. And I'm dropping the latitude and the longitude columns because even though these are numerical values, what they are representing is a particular location, right? So treating them as numbers, it doesn't make much sense. So I'm dropping them out and then leaving it out of this pair plot analysis.
Just one question: what is axis 0 and axis 1?
Okay. So when I say axis 1, I'm saying that this two particular data frames that I have should be combined along the columns. So I'm saying this, add this column cal housing the target as another column. Right? If I did not specify that, axis by default would be 0. It would be trying to add it as new row, right? So it would try to add these values as new rows instead of adding it as a new column. So if I just did this, so let it create a plot. Yeah. So I'll show you what a pair plot is. So so what drop does is drop will just remove the columns that you are specifying, right? And it will return you the rest of the columns. So that's what drop does. So yeah, so this is the output of the pair plot function. So here, we have a 2D matrix basically. So we have the 8, 9, seven variables, right? Yeah, because we added the target variable and we dropped latitude, longitude. So we have seven variables. So those seven variables are there, on both the x-axis and the y-axis. And for each combination of the variables, you will get a scatter plot of those, data points. It's for example how, the median income changes as a function of the median, house value. So we are seeing some positive association, between these two variables, right? So our target variable is actually the median house value, right? So this last row as well as this last column corresponds to, our target variable. So we can look at any one of that. So here we see that the median income in that particular block has a positive association with the median house value, right? So which means that more people with a higher, income, the house prices of those, people would be expected to be higher, right? So that's what we are seeing here, some positive association, but we are not seeing any clear pattern with respect to the house age, right? So irrespective of house age, the median income value, varies largely. So there is no particular, pattern that we are seeing here, and so on. So we can use such, analysis to pick your variables, right? So variables that have a positive, a very strong, effect, would help you in predicting better. But not seeing any relationship in the scatter plot doesn't mean that variable is useful. So the scatter plot is only telling you if there is any particular, association by that variable alone, right? So, but it could have some interactive effect with some other variable. So it doesn't hurt for you to try, including that variable even if it doesn't show any effect on the scatter plot. Yeah, so coming back to what the axis equal to 1 does. So here when I didn't specify axis equal to 1, it means that axis is equal to 0. And what it did is it kept, cal housing data first, right? So the 20,000 odd observations. And then this cal housing target is added as new rows, right? So, and then for the old, for the other columns, it had put NaN, and then it added these target variable as new rows, here, and then for the rest of the observation it had put NaN there. So we do not want this. So we want these values to be appended as the new columns for these same observations. So that's why I had given axis is equal to 1.
Okay. Got
Yeah. Okay. And
one more question is that
yeah.
is the target, whatever the target is, so
Mhm.
is the model telling me that cal housing at what is the target in this particular data frame, that
Yeah, so far we have not built the model yet. So these are the actual values. So the cal housing target, which is the median house value. So this is the actual value or actual median value of the house prices in that particular block. So these are known to us. So we are
no, my
Mhm.
question is very specific, that
Mhm.
what is the objective, means how did
Yeah.
you find that med house val is the target variable or the target variable for us to find out in this training model.
Yeah, so that is the problem definition. So you come up with that. So that is the objective that we have come up with. So before building the model, so the problem was to, for us is to do this, right? So you define this based on your requirements. So here we wanted to predict the house value because if suppose in a new region we want to predict, what will be the house price, right? So in that case then we can use the model to, by specifying, its location and then the characteristics of the houses, we can predict what would be the median house value in a new location. So that's the objective that we wanted, right? So this does not, this has nothing to do with the model that you use. So this is based on your requirements and the objectives and the goal that you're trying to achieve. So you define that first, then collect the data to achieve that particular goal, and then you build the model to make this predictions. So here we are assuming all that
Actually
is done.
the axis 1 and axis 0, it's I didn't get it clearly after explaining also. So if
Okay.
in case any other method that you can use to make it very clear.
So I'll just take two particular columns to illustrate this. Okay, I'm just taking this house age variable, and then let's take one more. median income. We have these two pandas series, right? So these are now two different variables, but I want these to be in a single data frame. Okay, so that's what I'm trying to achieve here. So I have to append these two as two separate columns of a single data frame. So to do that, we can use the concat function. So to concat, we will say what are the variables that we need to concatenate. So I'm putting these two variables here. And then if I say axis is equal to 0, so what will happen here? It is going to concatenate these two vertically, right? So it's going to take the house age variable. It will just put those first, right? So because we had 20,639, so the first 20,000 actually 640 20,640 observations would be corresponding to the house age variable, and then from 20,641 onwards, the next set of observations will be corresponding to the median income, right? So it is stacking them vertically when we say axis is equal to 0. So along the row axis, it is doing the stacking, right? So but we did not want this. We want these two variables to be stacked side by side, right? So we want them to be stacked horizontally. So to do that, we have to say axis is equal to 1. So in this case, instead of stacking them vertically, these two variables are stacked horizontally. Did you get this?
Yeah, got to know. Yeah, got to know.
Yeah.
Thank you so much.
Okay. So once we have done this, now let's also look at the correlation. So even though the pair plot gives us a rough idea, so we can quantify them numerically. So I'm just calling the data dot correlation function, and this will give you a matrix, basically a 2 by 2 matrix, same 2 by 2 matrix. And all we are interested in at this point is what is the correlation with the target variable, which is median house value. And if we see this again, what we get the same inference from the plot. The median house income has a strong linear correlation, right, with the house value, just 0.68, whereas the other variables are not as strongly correlated, right? We have very marginal correlations, associations that we are seeing with the target variable. But we'll still go ahead and use all our features and see how well the model performs. So we have to still do the train test split, right? So it is the same procedure that we saw for the classification, doesn't change. Right, so we are passing in the input features, we are passing in the target variable, and I'm still keeping the 30% as a test size and some random state for reproducibility. And yeah, so we got the split. So approximately exactly 14,448 observations in the training data and 6,192 observations in the test data. These are randomly picked, right? And for this regression problem, again, we'll be looking at two models. One is a linear regression, which is going to use ordinary least squares method, and then a decision tree regressor, right? So the same algorithm, the same method that we saw for classification, there is a regressor counterpart to it. So it's a decision tree regressor estimator. So for the linear regression, so again, because the APIs are the same, right? So consistent pattern. So as we saw earlier, we just have to change the estimator object, and then we can use the same fit and predict pattern, right? So I'm creating a linear regression, estimator object, and then calling the fit method, passing in the training data. So we have fit the model, and to make the predictions, we are calling the predict function and passing in the test data. So making the predictions for the test observations. So because this is a regression problem, right? So our output is continuous, right? So these are the predicted median house values, right? So again in hundreds of thousands, because our input was also in hundreds of thousands. So it's in the same scale. So to evaluate the regression model, so we'll use different metrics. So accuracy doesn't make sense in the case of a regression problem, because very rarely you can match exactly the predicted value to the observed value, right? So because these are floating point numbers, matching them exactly would be very difficult, right? So accuracy would not make much sense because 2.71, and if 2.71 was the original value, and if the model predicted 2.72, if you use accuracy metric, it's just a binary outcome, right? True or false, correct match or not matched. But for 2.7 and 2.72 are pretty close, right? So it's not very it's a large error compared to 2.7 versus 5. So we'll use some other metrics for the regression problem. So one is a R squared. So R squared tells you how much of the variability in your data is explained by your model. So it ranges from 0 to 1, right? So and values closer to 1 are better. So in this case, we are getting a R square value of 0.6, which is pretty decent for a linear regression model. And the other metric that we are going to look at is the root mean squared error. So what does root mean squared error is? So error is nothing but, so you have a particular value, right? So y, let's call y is the uh, observed value or the true value, and let's say y hat is the model's predicted value. So what is error? Error, or it's also called residual. So it is nothing but the difference between the predicted value and the observed value and the predicted value. So y minus y hat. And what we are going to do in roots mean squared error is basically for each observation. So we are going to look at what the error is. We are going to square this error, right? So error will be square, and then we are going to sum up, take the mean value of the squared error, right? So for all the observations, we are going to take a sum of these errors and then divided by the number of observations. So this is nothing but your mean squared error. Okay, so we are taking the mean value of the squared errors, and in the root mean squared error, we are going to look at the square root of the mean squared error, right? So why are we doing this? Because because the error, when you're looking at the error, it is in the same dimension, right? So if this was say dollars, right? So the error is also in the same unit, dollars, but when you're squaring it, the unit is now in dollar squared, right? So the mean squared error is also in the same unit, dollar squared, but when you take square root, it comes back into the original scale, which will be in dollars, right? So it will be easier to make sense of it in the original units. So that's why we are going to look at the root mean squared error. So what it means is a root mean squared error of 0.73 is, on an average, the error is about 0.73 or $73,000. $73,000 is the average error for across the different observations that we have made, different predictions that we have made. Okay, so again, values closer to 0 would mean that a better prediction. So from the linear regression model, we are seeing that it's giving a R square of 0.6 and a root mean squared error of 0.73. Now let's try a decision tree regressor on the same data set. So again, I just have to change the estimator object that I'm using. So instead of linear regression, I'm going to call the decision tree regressor and fit it on the same data, make predictions on the test data. So these are the predicted values from the decision tree regressor, and then just going to evaluate it in the same way. I'm looking at the root R squared, so which is 0.59, and the root mean squared error of 0.73. So if we compare it with the linear regression, it's not doing better, right? So the linear model is very slightly better, and these performances are very comparable, right? So we are not getting anything better by using the decision tree regressor, but we have to remember that we have used the default parameters. As we saw earlier, there are a number of parameters that are available for each estimators, and the optimal value of those parameters would depend, is highly specific to the data set that you will use, right? So it's necessary that we tune these models. So let's quickly look at how this model is performing on the training data also. So using the same methods, instead of looking at the test data, so we can use this training data as well. All right. And if you look at the performance on the training data, we see that it's giving a very ideal performance, right? So R square of 1, which is the best value that we can expect, and a root mean squared error of 0, right? So which means the model is able to predict exactly on the training data, right? But if we look at the same model applied on the test data, we see a poorer performance, right? R square of zero point 0.6 and an error of 0.73. So this large gap between the training performance and the test performance indicates what we call as overfitting, right? So there is this term called overfitting. So which means that the model is basically like memorizing your training data, right? So so if you give the same observation that it saw earlier when it is training, it is able to make a good prediction for those observations. But when you give it a new data that it has not seen earlier, it is not able to predict as well, right? So this is the case of overfitting. So we need to control the parameters of the model in order to reduce the effect of this overfitting. Basically, we want the training and the test performance to be reasonably close to each other, right? So that we know that the model will be able to generalize well to other unseen observations. So how do we get this bring this overfitting down? So to do that, we have this concept of hyperparameter tuning. So hyperparameters are nothing but the different parameters that are there for the each model, and we want to find the optimal values for this, right? So that the optimal value would depend on the data set. So for each data set that we are using, we have to tune it and find the best values. And to do this, there are again different techniques that are available. Again, scikit-learn itself provides multiple techniques. The two popular ones are the grid search and the random search. Okay, and again for doing this, we'll be using a technique called cross validation. So you can read about these things in detail in the links that I have given here. So the general idea is this. So we have a data set, right? So in this case, the house pricing data set, and we split that into a training data part and a test data part. And what we will do now is, once we have the training data, so we have the different parameters that are available to our model, right? So we will try different combinations of these parameters, and we'll use the cross validation technique on the training data, and we'll choose which set of parameters gives us the best predictive performance on the training data, right? The cross validated performance. And once we have found out what is the best set of parameter values that are working well, so we'll go back, use these instead of the default parameters, we'll use this best set of parameters and then retrain the model. And using this final model, we'll be evaluating it on the test data, right? So this is the general framework for hyperparameter tuning that we will follow. Okay, so first, I'll illustrate this using the decision tree regressor. But again, this is applicable for the other estimators as well. But the parameter that you will tune and the values that you will try would be varying depending on the estimator. You have to look into the documentation for that particular estimator to see what are the parameters that are available. But the process would be the same. So if you look at the decision tree regressor, it has a number of parameters: the criterion, the splitter, the maximum depth, and so on. So each parameter will have different values that it can take, and it will have different impacts on how the model will perform. For example, if you look at the criterion, so there are different values like squared error, which is the default, absolute error, there is Friedman MSE, and so on. So what squared error does is, the objective function is to reduce the mean squared error, right? So as we saw how to calculate the squared errors, the mean squared errors. So the objective in a squared error is to reduce, the mean squared error across the different observations. Whereas if you use the absolute error, so you'll be trying to reduce the median, right? So instead of the mean of the squared errors, you'll be trying to reduce the absolute value of the errors, right? So that's how the criterion affects the model depending on what the loss function or the objective function is. And there is this parameter called the max depth. So this decision tree models will try to basically come up with rules of segmenting your data into different categories, right? And the larger the depth that you choose, the more segmentations that the model will carry out. And typically, with the higher depth, the model is more prone to overfitting, right? So controlling this max depth is one of the important ways in which we can control the generalizability of the model. So and there are other parameters. You can again go through this later of what the different values that you can give them, and how it will affect the performance of the model. So as an example, I'm going to look at these two parameters for tuning, the criterion and the maximum depth. Right, so to use the hyperparameter tuning in scikit-learn, so you have to first create a grid of parameters, right? So basically a dictionary whose keys will be the name of the parameters, and the values would be the different values that are the combinations of values that the particular variable can take, parameter can take. So here criterion has two values that we can give it. One is squared error, another is absolute error. And for max depth, it can take integer values or it can take none as well, in which case there is no limit on the depth. So I'm going to try these different values. So 10, 20, 30, 40, and 50. Right. So I'm just creating this parameter grid, as a dictionary. And to do this,
Can you please explain the Can you please explain the concept of overfitting once again, because it is not clear.
So overfitting is when model performs well on the training data, but the same level of performance is not seen on the testing data, right? So which means that there is a large gap between your training score and your test score, right? So which means that the model has not learned the actual patterns in the data, but it has learned the peculiarities that is there in your training data, right? So for a particular combination of a variable, it has learned what how the prices are, but those patterns are not actually general patterns, right? So that's why we are seeing that when the model applies those rules to an unseen data, it is not able to get the correct predictions. So which means that what the model has learned is highly specific to the observations in your training data, right? So that's why this gap is there. So what we want is we want the model to be able to learn the true the relationships, or as closely as possible the true relationship, so that the model when applied on a test set is also performing better. So we want this gap that we are seeing here to be smaller.
It means it is showing as 0.59 and 1.
Yeah.
That is the difference, are you saying, right?
Yeah. So in the test set, it is able to only explain like 60% of the variation that we see in the target variable, whereas in the training data, it is able to explain 100% of the variation, which means it's predicting perfectly on the training data, but on the test data, it is not able to perform as well as we see in the training data. So
Sir, but in the training data, the machine has learned the based on the training data, right? So it will give you 100% performance only, right?
Yeah, not always 100%. In some data sets, it will be close to perfect if it is overfitting, right? But we do not want that. So you want actually this performance that we are seeing here to be actually on the test set, right? So generally the training performance will be greater than the testing performance because the model has already seen this. But what we want to make sure is it should not be terrible on the test set itself, because that makes the model useless, right? So if it performs too well on the training data but not on the test data, then there's not much use of it, right? Because the training data we have already seen it. The purpose of us building here is for the predictive purpose, right? So which is for unseen data where we do not know the actual the target values. So we want the model to be good on those observations, right? So therefore we want the performance in the test set to be higher. So here we know that it will perform well on the training data because it has already seen that, but we do not want the gap to be larger. So that's the objective.
Okay, and so for that reason, to minimize that gap, are we using that hyperparameter tuning?
Yeah. To bring that gap down, we are going to tune the hyperparameter.
Okay.
Yeah. So in this example, I'm just showing the two parameters, criterion and max depth, but you can use other parameters as well, and you can also choose different values that you want. And the technique that I'm illustrating here is the grid search. So what a grid search does is, you imagine this to be a grid of values, right? So because we have two criterion, right? So a grid search would check all the different possible combinations of the hyperparameters. For example, with squared error and max depth of none, and squared error with max depth of 10, max depth 20, 30, 40, 50, and so on. And then with absolute error and max depth of none, absolute error with 10, 20, 30, 40, 50, and so on. So it will do all these different combinations, right? So we have 6 values for max depth, to be tried and 2 values was criterion, right? So 6 into 2, so 12 unique combinations are possible, right? And a grid search will try all those different combinations that are possible, right? So basically it will try to build 12 different models, decision tree regressors, right? And each model will have one unique combination of these parameter values. And for each of these model, it will try to do it will try to evaluate how good it is using a five-fold cross validation, because we are saying CV is equal to 5. And the scoring method that we are using is the mean squared error and the negative of it, right? Which means that lower error would mean a better filter. And doing this, so using this is just as fitting the model, the regular model. We just have to wrap this decision tree estimator in a grid search CV function, and then once we do that, so we can call this new object and the fit method on it do this hyperparameter tuning. So it will take some time depending on your data set, right? So if you have a large number of large size of grid, also large number of variables, this will take a lot of time to train, right? So you can adjust that by either reducing your search space, or by reducing the number of cross validation folds that you have. So in this, since this is relatively a smaller set of data, it should not take much time. So while it is running, if you have any questions, feel free to ask. Okay. Let's just wait for it to complete. Okay, so the hyperparameter tuning is done. So this fit function is returned, and once this fit is done, so we'll be able to see which combination of the parameters gave us the best best performance, and we can access that using the dot best params attribute. Okay, and also what is the corresponding score, right? So the scoring that we used was the negative of the mean squared error, and what was the best score that we had from this combination of the hyperparameters. So we can get that using the dot best score attribute of this the estimator object. And if I run this, so what we have seen is using an absolute error criterion instead of the default squared error, and a max depth of 10 gave us the best performance, and the best performance MSE was 0.45, right? So this is the best that we have been able to achieve for this data set with this combination of the hyperparameters, right? So if you use other variables or different limits, so you may able to achieve even better performances. But for this particular combination, so the best that we can do is using an absolute error as the criteria and a max depth of 10. So now we can again use these values and then retrain the model, or you can directly take the estimator that from the grid search. Okay, so that you can get it by calling the dot best estimator. So the other way is you have to retrain the model. So retrain the model, you will be creating this class, and then when creating it, you will be passing in these optimal values that we have found, right? So you can do it this way, and then fit the model again. should be equal to should not be a string. Yeah. So we can fit the model again, using the best values that you have found so far, or you can just directly get the best estimator attribute, so which will again give you the same, the model that was fit using that same set of optimal parameters. And using that, we are going to predict it on the test set. And here we are seeing that the root mean squared error with this best model on the test set is now 0.66. So if you look at the earlier value, the earlier value with the default parameters gave us a RMSE of 0.73. Now we have reduced it from 0.73 to 0.66, right? So we have improved the prediction performance just by optimizing the criterion and the max depth, right? So by choosing by looking at the other parameters, we may able to get even better performance, but we will not go further with that, because this was just to illustrate how we can achieve this. And now if you look at what is the performance on the training data, we see that it has now come down, instead of being perfect as earlier. So the R square has reduced from 1 to 0.8, and RMSE from 0 it has increased to 0.52, and therefore the gap with the test performance has come down, right? So we can say that the overfitting has reduced. So let's just see the R square as well on the test data. So R square is 0.767, and on the training data is 0.8 now. So the gap is much smaller than what we had earlier. So the model is now able to learn better patterns or features from the training data, so that it is able to generalize well to the unseen test data, right? So this is an improved model with the hyperparameter tuning. And also scikit-learn provides you with some tools to visualize, to understand how these models work. Especially for decision trees, it's easier to visualize them. For example, we can plot the actual decision tree that the model came up with. Even though the optimal parameter was 10, right? So it can go up to a depth of 10. So because it's difficult to visualize a depth of up to 10, I'm just limiting the depth to only 2 levels, and then we can see how the model has come up with the splits. So what it is doing is it starts with a particular feature, right? So it is looking at the median income variable, and then it has come up with a threshold of 5.032, right? So all observations which are less than or equal to 5.032, so they go into one side of the tree, and the rest of the observations go into the other side of the tree. And then again it makes a split based on the median income itself into two splits, less than equal to 2.831 and greater than equal to 2.831. So, and then it is looking into the average number of rooms feature, and those observations that are less than 4.205, they go into one branch, and the other observation go into one branch. So like that, it will recursively be splitting the observations into these groups, and can go up to 10 levels, right? So this is level 0, then level 1, and so on. So it can go up to 10 levels. And so what is the output of the model? So if you give a new observation, basically, right, so it will go into one of these different branches, right? So because a new observation will have a particular value of median income, it would be either less than or equal to this or greater than this. And if it was less than or equal to this, it will go into this branch. Then again it will compare the median income value. Then depending on where it goes, suppose it goes here, then it will look at the average occupation value, and then it keeps going down until it ends up in a particular the last level of the node, so which is called as a leaf. So, and there will be some observations in the training data which will also be in that particular leaf node. And the prediction of the decision tree model, because the criterion is absolute error, would be the median of the target value for those group of observations, right? So that's how this decision tree model would make its prediction. And here it's very easy to interpret how the model is working, how it is making those predictions. And we had used the squared error criterion. So instead of predicting the median value of all the observations in the leaf node, it will give you the average value of all the observations as the prediction. right? So that's how we can visualize the decision trees. And to do this, you use the plot tree function from the tree module of sklearn. And also we can look at what are the importance of the different features, right? So which feature is able to is contributing more to the prediction performance of the model. So because we have seven eight different features in our data, so what we are seeing is the model is reliant more on the median income feature for making its prediction, right? So what we are seeing on the x-axis is basically the normalized value of the reduction in the error, right? So our error is the absolute error, right? So which variable is contributing more to reducing this absolute error of the observations. So we see that median income contributes to more than 50% of the error reduction. The next important feature for the model is the average occupancy, then the location of the block in the district. So these are the top features that the model uses, to in order to make the predictions, right? So relatively, the other features are less important for the model. So that's how we can get, which variables that the model is focusing more on, right? So also from the correlation, this also makes sense, right? So median income had the most strong association with the target variable, and therefore it's more useful in making these predictions. Any questions? And this importances you can get for the other models as well. So this is how you would interpret a model, and if you're not satisfactory with these results, you can go back and train the model with other combination of the parameters, or you can try other algorithms or models as well, like KNN and so on, and you can try different ones. Yeah, so these sessions are recorded and they'll be available on YouTube. Let me share the link for the channel. So the videos will be uploaded to this YouTube channel. You can look at it after the class. Are there any questions or doubts on how to use sklearn? I'm not sure what type of questions would come. Yeah, should be similar to what you're seeing in the assignments. So just familiarize yourself with that pattern. I think that would be the most likely one to come, right? So, yeah. So do the assignment and you should be fine. Yeah, I'm not sure objective or theory type, so you should contact NPTEL support. Yeah, so regarding exams, I'm not able to answer it because I'm not involved in that. So yeah, for all those, please direct those questions to NPTEL support team, so they'll be able to answer your questions related to exams. On which parameters the training data error will come? So is that the can you complete the question? So are you asking which parameters will reduce the training data error? Okay, so and it depends on the model that you are using. So you can try all the different parameters. So they have different effect on the model's performance. For example, if you want to bring the training data error, then for example, if you are looking at the max depth, then setting a value of none would be the best, right? So because you will get highly a tree which is unlimited in depth, right? So which means that in the ideal case you can have one leaf per training observation. So in that case, each observation would be perfectly predicted, right? So That's how we can bring the training data error, but it's not very useful, right? So because when you have such a deeper model, it may overfit on the training data and it will not generalize well. So what you should look to do is not just bring the training data error down, but bring both the training and the test data error down, keeping their values closer together. So that's what we are doing when you're doing the cross validation. So we are trying to find, the best combination of the parameter where the cross validation error is smaller. Yeah, by practicing, like we need to try different combinations and then tune the model in order to find out, which parameter combination works best for the data that we have. And again, it's highly data set specific as well. So if you change the data set, you have to again retune the model. Which is best, Collab, Spider, or Jupyter? Again, there is no specific thing. So whichever is better for you, try all the three, and then whichever works best for you, you can work with it. So the advantage with using these notebooks, Jupyter notebook, is that you'll be able to record your outputs along with your inputs, right? So as I'm showing here, it's able, you can easily refer back to this, the inputs and the outputs together, right? And also it's easier to show the results to somebody else as well. So that way it would be better to go with the notebooks, but even if you're using the other IDEs, that's fine too. With Google Colab, it's basically a version of the Jupyter Notebook only, right? So it's customized by Google. The advantage that you get there is you'll have access to GPUs, right? So if you don't have a GPU locally in your system, you'll be able to use the GPUs on the cloud. That will help you make the trainings faster when you're using larger data sets. What do you mean by accurate data? Accurate predictions? Yeah, the quality of your predictions, if you want more accurate prediction, it does depend on both the data set, the data set that you're using as well as the model that you're using, right? So you need a good quality data, right? So what do I mean by good quality data is having variables that are strongly related to your dependent variable, right? So that will help because it will help you explain how the target variable is changing, right? So there's the data aspect as well. You need good data, and there is also the model aspect as well, right? So the model also has to, for example, if you have a variable that is non-linearly related to a particular one. They say y is equal to x square. If you have some function like that and you're trying to use a linear regression model for it, you will not right, so you will not get a better fit, right? So by modeling y as a function of x using a linear model, you'll never be able to predict it accurately, right? So because the model is limited in what kind of functions it can um, represent, right? So the model also you have to choose appropriately, and you have to tune it for that particular data, and also the data also you should make sure that you have variables that are more associated or correlated with your target variable. Like in most cases, or in the real data sets, you'll have some variables which are highly correlated, and in some cases you'll have to do some feature engineering, right? So you have to derive or represent the data, the features in particular ways that are more useful for the model to learn the patterns. So it's both the data aspect as well as the model aspect that we need to take care in order to get better predictions. And again, there is no standard rule or anything, so you have to learn, and then you have to with experience you'll be able to try out different things and get better predictions, better models. So you have to use your knowledge about the data set that you're using and also the model that you're using in order to improve the predictions. What is the shortcut method to access syntax like dot coefficient? So there's no shortcut. So you just have to access the attribute for that particular variable. So the coefficients are available with the linear models, right? So for example, with the linear regression also we can get the coefficients. So we just have to uh, call the attribute. So by shortcut, do you mean how did I get this auto completion list? If you meant this auto completion list, so what in Jupyter notebook the shortcut is, once you have typed the object or the variable, after pressing putting the dot, if you press the tab key on Windows, it will give you a list of attributes and the functions that are associated with the object that you can call. So here we can get the coefficient for the linear regression model. Yeah. So you can try. So it should be available in all the notebooks. After the dot, you have to press the tab key. Yeah. So you can't know like which model will be better. So you have to try out different methods and see which works better. So, but there are some models which generally perform better than other models. For example, these decision trees are so the ensemble models like random forest, gradient boosted trees are basically extensions of your decision tree model, right? So those generally perform better than your decision trees, right? But you have to make sure that you're tuning the parameters correctly so that they do not overfit, because it is very easy to overfit with those ensemble models. So hyperparameter tuning is very necessary, but in general some models are generally better than the other models. So again, but it's not you can't say with certainty that this model will definitely perform better than the other one. So you have to try out the different ones for your data to know exactly which one is performing better. So you'll basically choose set of candidate models and then you try each of that and then decide which is performing better. Any other questions?
Will we have any session in the next week on Sunday or not?
Yeah. So we'll have one more session, which will be like a summary session again for 2 hours at the same time. So we'll just recap whatever we have seen so far in the 4 weeks. And if you have any specific doubts from the assignments or anything, those also we can discuss.
Okay.
About FDP, what do you mean by FDP? Yeah, so next week will be the last session. Faculty development program, I'm not aware of that. I'm not sure about this faculty development program. So contact NPTEL for that. So for the next week, we do not have anything specific, right? So new to be taught. So I would recommend that you go through all the videos, all the sessions that we had. Try out different things. So all the data sets, as I showed, you don't have to download it specifically. All are available with sklearn. So try out different things, and whatever doubts or questions you have, you can bring that up, and then the next session will cover all of that. Even from the previous sessions also, if you have any specific questions, we will address all of that in the next one. So please go through all this and then we'll have a better session if you have prepared.
So about KNN and random forest we have not gone through, right? KNN and random forest.
Yeah, it's not it's not possible for us to go through every algorithm in sklearn. right? This is the same pattern that you'll apply to all the models, regardless of which one you are choosing, right? So the parameters that are available to each model would be different. So you have to go through the documentations to learn what are the different parameters, what each of them does, but how to optimize them, how to fit the model, how to use the model for prediction and evaluation. So those whatever we have seen today, so that applies.
Okay.
So next session, so next week in the same time. So Sunday, next Sunday, I think that is 25th, right? Yeah, 25th, 6 p.m. will be the next session, the last session. Yeah, so the recorded sessions will be permanently available on YouTube. Even after the exams also, you can access these recorded sessions. Okay, also all the material that I'm using, right? So those are available in this link that I have shared. Right, so all the notebooks and the presentations that also that I've used in the earlier sessions, you can go through these as well. Okay, any other questions?
If we have any questions apart from the exam that while doing these things, so how can we reach out to you and get the doubts cleared? If in
Yeah,
case
so
you can
that's
share your email ID.
no, that's exactly the idea of having that next session, summary session. So whatever doubts you're getting, so just note it down and bring it to the next session. So we'll do that in the next session.
Sure, sure. Okay.
Or you can use the discussion forum as well. In the meanwhile, if you have something urgent, so those will be answered by the other TAs also. Okay, so if there are no further questions, so I think we can wrap up the session for today. Okay, so thank you all for attending. So we'll meet again next week for a summary of all the content. Okay, thank you.
Thank you so much, sir.